Hi, and welcome to SaaS Global Forum 2021. My name is Jason Brinkley, and today we're going to be talking about auditing algorithms and talking about some new tools to combat bias in artificial intelligence. So, a little bit about me. I'm a senior data scientist at Apt Associates. I lead a team that looks at a lot of different statistical models and machine learning algorithms for a wide variety of clients, including federal clients such as Medicare and the CDC. I also am a research affiliate at North Carolina Agri-Medicine Institute, and I'm active within the American Statistical Association and currently the president of the Southeast SAS Users Group. So, a few things before we get started. We are pre-recording, so I am actually partnering with myself. I'm in the chat, as you'll see below, and answering questions along the way. But if you have additional questions, my Twitter handle's at the end. Feel free to send me a direct message or to just post a question on Twitter, and I'm more than willing to come through and help answer different questions on this topic that I'm really interested in. So why are we here today? Well, we're really here to talk about artificial intelligence or machine learning. And I'm going to use the two terms interchangeably, and that's probably going to irritate a few people in the audience already. But this combined effort of looking at artificial intelligence or machine learning, it's seen some really rapid growth. And we also have seen a lot of stuff in the news cycle about how the algorithms that these things put together have increasingly seen a lot of biases, racial biases, gender biases, things of that sort. And we really don't quite know yet how to deal with all of these biases. We don't really have a unified, cohesive framework for saying, well, how do we make sure this doesn't happen? And I think it's important to know how we got here so that we can sort of think about how we're going to address it. So, the way this talk is going to be set up is kind of giving you a little bit of information as to like how we got here and maybe sort of the biggest reasons that I think why we got here, and then what people in the industry are doing about it, and then a call to action as to what else do we need in all of this. And we'll end with a few examples to where you can kind of see how this plays itself out in practice. So what did we do? Well, we used machines to build algorithms to help us do things that humans could not, were currently doing, but couldn't do at the complexity needed or at the speed needed for different scenarios. It's easy to get humans to do things that they can do maybe one or two at a time. But if you have to do this 10,000, 100,000, or a million times, whatever this thing is, it might be a lot easier to get a machine to do it. And so we train computers using artificial intelligence algorithms to sort of mimic what we want us to do as humans. And in the end, sometimes these things end up looking like Rube Goldberg machines, right? They're just sort of a complex fit of a whole bunch of things that seems to be carrying something out that's so extremely convoluted. And the reason for that and the mechanisms behind it is that the way we get a machine to learn how to do something is very different than the way we would teach a human to do the same thing. And so what happened in this framework where we developed these complex algorithms to help us perform these tasks is that we got a lot of instances where we started to see bias. Now, I've blatantly stolen this image from the link below, but I think it really sums it up kind of what you're seeing. You turn on the news, you look on the internet at different things, and you see all of these stories where companies replaced humans with algorithms and then found that they had racial or gender biases. And, people say these articles over and over and they start thinking to themselves, well, how could we have gotten this so wrong? And it isn't really that we got it wrong. What we did was gave those folks who developed those algorithms a set of rules by which to work. And so, we said we want to prioritize speed and accuracy. We want algorithms that are as accurate as humans and can be much faster than humans, can process a lot more information than humans, and do it as accurate as the humans who were doing it could do. And what we got on the other side of that is a little bit of buyer's remorse, because then we said, well, you never really, like in the meme there, you never said that it was going to be racist. And the math, the computer science, those algorithms, they're not built on a racist framework. Like the math behind these things are not racist, and they're not gender biased inherently. It's the application of those algorithms to real data and real settings. And that's really sort of the mirror that we've been holding up to ourselves on this, is that there were these biases in the system that we as humans were sort of self-correcting along the way. But then when we automated this into to have the computers take over, is when we started seeing these issues really sort of bubble up to the surface. And so what we have to do is come back to that framework. We have to say, okay, we don't want it to just be fast and accurate. We actually want you to do more stuff now, right? So I got to tell you, that's the reason why I'm here today, is that that's not an easy fix. There's not like a one size fits all for all of these. And what we've found is that for groups who are doing this a lot, the way you might fix gender biases might be different than how you fix racial biases or disparities against disabilities or things of that sort. But in general, there's sort of two ways to think about how we're going to fix these biases. Think of them in sort of two buckets. I'm going to start with the front end fixes, where we develop algorithms that don't really have those biases to begin with. And then we want to also think of sort of back end fixes. How do you identify and adjust those existing algorithms to remove those biases? And this is something we really need to think about because the research community has really spent a lot of time on that front end in the past few years. You started, the community has started asking for ethical AI or to get rid of gender biases or racial biases. And so the easiest mechanism to start with is let's not develop those algorithms to begin with. The downside to that is a lot of early adopters have already put together really good systems. And so if you say, well, we're just going to change the algorithm to where it doesn't do that, what you have in that mix is that the only solution is to throw the baby out with the bathwater, so to speak, that you scrap everything and start over for a less biased framework. And that doesn't always work for groups, right? If you've invested a lot of time and a lot of resources, then the question then becomes, what do you do, right? If I can't afford to implement something from scratch, how do I fix what I have? And that's a much bigger challenge, as we'll see in just a few minutes. So sort of taking those two pieces together, like front end fix, that back end fix, like what does that look like? We're kind of at the second stage of this discussion. And I want to introduce a few ideas that have sort of bubbled to the top, because when we start talking about gender biases or when we start talking about racial biases in the machine, these can manifest in a whole bunch of different ways. And so I'm going to talk about sort of three frameworks that are dealing with different things that we're already kind of looking at. And that'll give you kind of a sense of the scope of the problem, because it doesn't always manifest itself the same way with the same data or in the same problem. So I think if we talk about these alternative approaches, you can kind of see what problem each of these are trying to fix. And I think that that's an important starting point, because you're not going to eliminate all of this overnight. I think what we've come to a consensus on is that the machines are great. They're great at doing things at speed and at scale. But if we introduce human biases, then that bias gets propagated out into the machine and a lot of times gets amplified. But not all biases are the same biases, or the mechanisms behind those biases aren't always the same. So I want to give sort of three quick examples of where the field is going in that algorithmic development. And then we'll talk about a couple of instances on back-end fixes, where this is, to me, and the reason why I'm here today, is to talk about the fact that this is an area where we need a lot of growth. We need project managers and business developers and subject matter experts to really identify what's going on with these bad algorithms. And then we need statisticians, computer scientists, data scientists, the entire suite of math nerds to kind of come in and help develop new metrics, new techniques, so that we can fix those things. Because even with the frameworks that we're going to be discussing, each of them are responding to this idea of bias in different directions. And there can be something else that happens down the road that those same algorithms will have to pivot in terms of trying to fix. So we're always going to be developing new algorithms. Like that's always on the horizon. But we need the metrics as well, because this is really where we demonstrate the infancy that is machine learning, that we still haven't really fully got there yet. We've been so focused on making algorithms that this idea of evaluating their performance and really getting under the hood has been challenging. And in fact, in a lot of cases, AI has gotten a bad rep for being something of a black box. Right? That's a term that we use all the time in this area. How do we not have a black box in all of this? And I think having more of this back-end piece helps us demystify those pieces. And we're just still not there yet. Okay, moving on. Let's talk about the new AI. So what does that look like? There are a whole bunch of different ones that different teams are developing and doing stuff. I'm going to give you kind of a flavor of that. And the key in all of this is trying to figure out what is it that's biased and what is it that you have to fix. And you're like, well, it's just bias, right? It's just racism. Like, isn't all racism the same racism, or gender bias all the same gender bias? No, they manifest in a couple of different ways. So let me give you the first example. Let's talk about interpretable machine learning. So these are algorithms that humans can explain. So if you're familiar with the sort of foundations of machine learning, a lot of that came from the beginnings of tree models, decision trees, and things of that sort, these sort of classic MART or BART trees. What I'm talking about here in interpretable machine learning is going back to those original ideas that were sort of at the foundation of of machine learning in terms of stuff, and really giving it a shot in the arm. So I think see the paper that I put together for some links on this. I think as one starting point, I would check out Dr. Cynthia Rudin's work at Duke. And the idea is, instead of this being a black box where we don't really know where the racism is coming in or the gender biases are coming in, let's develop an algorithm that's very interpretable. That's really a set of lists or rules that we can, a set of discrete steps for making decisions. And we'll let the machines decide on what those decisions lists, what the list or the trees and all of that look like. And really sort of revisiting that foundation idea. And that can be a really good fix for those biases, right? That in that you don't have, you have something that's interpretable, something that you can open up the hood on, lots of people can look at. It's a really good avenue for starting to fix some of this, because you'll know where the biases are if you can actually look at the set of decision rules that are being made in all of this. By contrast, something like Humble AI would be developing the same algorithms and then giving it a comfort zone, giving it sort of a place to say, okay, this is where you're allowed to make decisions. And once you get kind of out of that comfort zone, then you have to stop and let the humans take over. And this is another route where you're sort of putting boundaries on where the machines can do their work and make their decisions. And when they get a scenario that could put them in that like gender bias category or that racist category or other categories, the machines kind of stop and say, this is not a usual circumstance for me. This is the kind of place where we need the humans to take over. And that humility means that you're not automating everything. And that can also be a great mechanism for identifying and reducing that bias. I would suggest that you look at the work by GE Digital, led by Colin Paris. Quick Google searches, you will find all kinds of stuff on this, but also see the paper for more details. So then we talk about FAIR algorithms, and those are the ones that are really getting the most traction. And I really like the work of Dr. Sherry Rose at Stanford. And the idea here is that we impose a penalty in the algorithms that we develop and say, we want the predictions, we want the accuracy to be consistent across all of these levels. So if your algorithm is really performing well on whites, but does not do so well on non-whites, then you have to penalize the work that you're doing on whites so that they're equivalent across the board. And so you set up the classes under consideration, and then you tell the algorithms, hey, we're going to impose these additional aspects to ensure it's sort of fair across the way. And so that's a third mechanism for sort of doing that. Now, not all of those will deploy the same way in all the circumstances. You can't maybe always be humble. You may not always be interpretable, right? You may not be able to be fair, and we'll see some examples of that in just a minute. But once you've got an algorithm developed, like how do you assess? How do you know whether or not you actually have bias in the machine? And I think that's a good starting point, because I think a lot of people only see it when Axios or ProPublica or one of the major news outlets identifies, hey, your algorithm is biased. So we need metrics, and that really gets us to the back end of some of this. So here's an example of one of the metrics, and this one you can kind of start to see. I'm going to get mathy for a second on some of this, but thinking this through, that like you have a binary outcome, success or fail, and then you've got a binary class of disparity, white, non-white, male, female. Then you can calculate something called a disparate impact score, which would be the ratio of your predictions for success between the two groups, right? This is super interesting in that you can sort of look at the impact of your predictions between these different groups, but it's really only limited to a few scenarios. I have a paper here where you can get started in looking at all of that. This is just one metric. We need tons more, and you can kind of see, well, what if I don't fall into just white or non-white? What if I want to look across a racial continuum, a larger set of groupings, right? Or if I don't just have success and fail? What if I can't boil it down that way? There's a lot of work that needs to be done here. So sort of moving on, like, what's the root cause of scenarios where we don't know that we have this bias, or if we have differences across these groups? So I might have an algorithm that I think performs pretty well. Somebody tells me it's racist, and then I have to replace it with another algorithm. So this takes me to get to another scenario where I have to figure out how to replace one with the other. So in other scenarios, you might need to compare algorithms. So looking at metrics is great once you actually have an algorithm that you want to assess. But what happens if your algorithm's already been assessed and you found it to be biased and you need to replace it with another algorithm? Well, that takes you into another problem where we come back to the impact of algorithm replacement with another algorithm and assessing whether or not you're losing a lot of information or capacity in replacing one algorithm with the other. So we're going to take a scenario here where we have an algorithm, and what I've got here is 2 million instances on something that, or a million instances, sorry, on something that this algorithm has been developed to look at success or failures. And this is just a toy example. But you can kind of see that this is a general setting that we would develop AI in, that we have some training data, we know where the failures are, we know where their successes are. And this is sort of looking at the diamond in the rough, right? You have a million instances and only 2,000 successes. And just about anybody that compares algorithms would tell you that this is a pretty good algorithm for this, because we get about 75% out of those 2,000 successes. This algorithm can find them. But then let's say you find out that this is biased and you have to sort of figure out what to do next. And you train up another algorithm. Where we're losing out is we don't have math that really looks at the comparisons between these two algorithms together. So for instance, let's say I develop a whole nother algorithm that performs exactly the same way. Okay, so I now have two algorithms that are sort of built on different things. One's determined to be biased, the other one's not, but they have sort of the same success rate. Well, what would that look like in practice? Well, what you might want to have to do is to compare the two algorithms. And that's where you start to see some of this fall apart. That if algorithm A was built on biases, then some of their successes was linked to those biases that it had to lean into to make that happen. So you could actually have two algorithms that both independently perform well, but that when you stack them up, they don't agree much. So the two algorithms, they commonly can predict 1,000 of your 2,000 successes, but the 500 to 1 algorithm gets right. Maybe the 500 is that the other algorithm picks up. Now, normally we would stack these together and ensemble them and sort of take the best of both worlds. But in the scenario where you have gender or racial or whatever biases, you have to ditch the old algorithm because it's doing all of those things. What we don't actually have is good math in this scenario to sort of drive that agreement, because what I want is the algorithm match up just on these parts right here where they were all being successful. And all of the math that we've developed for all this leans into the idea that you predicted 99% of your successes, and that you're predicting failures, right? So that framework is off, because lots of businesses would say, I can tell you the failures outright. What I need to know are the successes. And we did not build any of these algorithms so that you can make those comparisons. So we need new math in this area. All right, so that's metrics. Let's talk a little bit about techniques. So here's one. It's not really a thing yet. It's something some colleagues and I are working on, but think of sort of crossover assessment. So imagine that you've got these two competitor algorithms and you want to measure this agreement. One thing that you could do is you could run the results from algorithm A through algorithm B and vice versa, and then make those comparisons. And you say, well, when would that work? When could I take two algorithms and run the result on one through the other? I'll give you a scenario in just a few minutes, okay? So this won't work with everything, but this is a really good example in sort of language models and things like that. So that actually gets us to this idea of working in practical settings. So I would say we don't want the perfect to be the enemy of the good. So none of the algorithms or assessment mechanisms discussed here are perfect. So let's talk about a couple of different scenarios and think about how we can implement either some interpretability or some humility or some fairness, or how we have to get creative with our assessment. And then, as always, I think your teams need to start having diverse points of view, because what we found internally is that if you don't have the perspective to know what to look for, then you're not going to be able to identify it in the early development or the deployment. So let's take an example being criminal sentencing. This is a great example from the perspective that the issues are systemic. So we see a lot of research that shows that there is some bias in criminal sentencing, but even if we come through and we deploy an algorithm that sort of fixes the criminal sentencing issues, you still have disparities up the criminal chain, right? In terms of imbalances of folks that are breaking the law or being arrested or being evaluated in a fair trial, all of those things. So fixing just the one component of that system doesn't fix the entire chain of events. And it's not just criminal justice where we see some of this. We see it manifest in chronic kidney disease on the health side of things. Once folks get on an organ donation list, we find that those can tend to be fairly fair, depending on the state and how all of that goes. It's the getting onto the organ transplant list that can create disparity. So even if you fix the one piece of that system, those disparities can bring forward. You get a higher propensity to be in some of those places. And so that's an issue where the systemic differences run deep. And so developing a fair algorithm is going to be very difficult because you have such an extreme imbalance to begin with, right? So that's where things start to become a little challenging. Let's take another example. This is one that my team has worked on in terms of bot detection. We did used vaccine-related Twitter content to put together a language model and for vaccine discussion on social media. And one of the things that came up was discussion about bots. We didn't want the bot language to drive our language models. So we pulled two public-facing Twitter bot detection algorithms from the web to see whether or not our Twitter handles were bots or not. They were complete in non-agreement. The Kappa slide that I just showed earlier, that's an example of what happened there. Those two algorithms, they did not hardly agree on any of the Twitter handles that we gave them as being bots or not. And the conclusion that we made, even after all this intense evaluation, was that bot-like behavior means that the evaluators and the creators can access that means of detection. And so actually to reduce that bias, the best thing might be to have an algorithm that's proprietary and not be open. It was a really good sort of case against sort of open source algorithms for things. Let me give you one last example. I'm thinking about public records in terms of redaction. We do this a lot as well. And here's the example where that crossover really sort of plays a role. So if you try to look at text like Lou Gehrig is a great ball player versus he died of Lou Gehrig's disease, the second one, you might want to redact the term Lou Gehrig in because that can identify somebody specifically. Lots of people have the first idea, you know, that Lou Gehrig's a great ball player. But in terms of training a model to look at those things, you can see that there's a difference in that context. And names are one of those areas where we've already started to see some literature that points to challenges in redacting sort of non-white names. So it's hard to sort of compare those algorithms because they redact different words and in different places. And here's this place where the team that I've been working with, have been experimenting with this crossover assessment. Redacted one algorithm and then cross over and redacted the other algorithm, and then vice versa. And then you can kind of assess who is redacting where and where those gaps are. So that's another sort of simple tool that we're exploring sort of in practice. So sort of tying it all together in terms of things, there's a lot of work yet to do in this area. We need new metrics. We need new techniques. We need to realize that not every scenario is the same. We need to recognize that what we do for criminal justice is probably going to be different than what we do for environment, different than what we do in manufacturing. So there's a lot of room for growth. And so I'm really hoping that there's a lot of folks that are going to get inspired to work in this realm. And feel free to check out the paper that accompanies this for more information. My Twitter handle's down at the bottom. Feel free to reach out there. So is my email address. I'm looking forward to hearing feedback from everybody. Thank you so much.